Hi, hello. My name is Eddie. I'm from Raysolve Optoelectronics. We are working on the micro LED and its full color micro display for AR glasses. And here is our full color micro LED display demo. It's very bright. Yeah, PowerMatch 1 is our series name. Yeah, there's the full color actually. And there we can see the full color projection demo. Yeah, this full color projection uses a very small, tiny light engine. The light engine size is 0.18 cc. It's the smallest full color light engine in the world.
Wow.
And current resolution is 320 times 240 QVGA. Right now we are shipping some samples to our potential customers.
Yeah.
In China and also in other countries.
Yeah. Because it's still very new, right?
Yeah, it's a new technology, and we do all the color pixels on the same chip. It's a single chip solution.
In the subreddit where I share the news, right? People always asking, why is it still only green? We want full color. When do you think we can see full color smart glasses?
Yeah, I think in next year, 2026, we may see some more mature full color micro LED solution for the AR glasses. And I think we may be the first one can launch some more meaningful full color display for the market. I hope so.
Yeah. Yeah, we're looking forward to it. But still, monochrome will always play a big role, right, for the foreseeable future.
Yeah. In the next few years, monochrome may have their market needs because it's maybe cheaper and also it can provide high brightness in current situation.
Yeah.
Yeah.
Until the optics get more improved, right? Because they need to be more efficient too.
Yeah. Actually, we see waveguide efficiency is keep improving.
Yeah.
And so we think that in maybe 1 to 2 years, we will have some good optical solutions for AR glasses.
And how bright are these displays?
In our current situations, the maximum brightness from the display is 500K nits. That's the current maximum display brightness.
Yeah,
and
that's for green or for what?
For the full color.
Oh, wow.
Full color. So we target about 1,000K nits at the end of this year. So we keep improving the light extraction of the whole devices.
Yeah. And what kind of optics can you use with this brightness that you're targeting? So because now we see even OLED coupled with like diffractive waveguide. So like 50,000 nits gets them like 300 nits.
It's not bright
it's
enough.
Not bright enough, right?
MicroLED is necessary for AR glasses.
Yeah.
If
for outside especially.
Yeah. For AR glasses, they must need the diffractive waveguide.
Yeah.
And the diffractive waveguide, the efficiency is low, so MicroLED is the only way to work with waveguide techniques.
Yeah. So your customers are not that interested in, let's say, like reflective waveguide.
I think there's some problem of the refractive waveguide. The mass production they still have some problem.
Yeah.
And also the yield problem of the application.
Yeah.
And actually, we have the AR glasses demos, and we use
let's go there.
Our micro display and also the diffractive waveguide. Yeah, that's the AR glasses demo.
Very popular.
Yeah, this is the first AR glasses prototype use our single chip solutions, full color micro LED, and it works with SRG diffractive waveguide.
This is similar to what's in HoloLens, let's say.
Yeah,
I think
HoloLens use the diffractive waveguide.
Yeah.
But the light engine is not micro LED.
The light engine is different. Yeah.
It's different. I think HoloLens is using LBS.
LBS. Yeah. Not that popular anymore.
Yeah. We currently use 8-inch wafer process to do the micro LED fabrication. It's the 8-inch wafer.
Yeah.
That's how we make the micro LED.
So everyone started maybe with a 4-inch,
yeah,
and now we're going to 8-inch, right?
it is, and it's more competitive using
Yeah.
the 8-inch wafer process. We can make more
chips.
micro display chips on the same wafer.
Yeah.
Just example, for one 3-inch micro display in one 8-inch wafer, we can make over 1,500 chips in one single wafer.
Yeah.
It's more productive.
Yeah. And is any micro LED company using more than 8-inch? 8-inch is the standard
I
now,
think
right?
8-inch is the largest.
Yeah.
Maybe later on, then it will go to 12-inch wafer.
And that's where the OLED is at the moment, right?
Yeah. We are building up our capacity currently, and our headquarters in Suzhou, China, is R&D facility.
Yeah.
And we are working on the mass production in different cities in China. And so in current situation, we just start the productions phase, and I hopefully in the early next years we will have the production ready for the market for our customer.
Yeah.
Yeah.
So maybe like 2027, maybe then the capacity will be high enough for really mass market.
Yeah. I think 2027 is a very critical years for the AR markets, including waveguide, including micro LED.
Yeah.
At that time, the technology will be much more mature for the customers.
Yeah. So full color at the moment, people are still looking at alternatives, right? Like LCOS. So maybe in 2027, micro LED will be ready to.
I think micro LED will be the dominant technology in the markets.
Yeah.
Yeah, because the LCOS have their own problems, the light leakage, and also the power efficiency problem.
How much energy do your displays take? How much do you need to power them?
In our current chips, and when we set the APL, every pixel level at 10%, and the power consumption is around 200 milliwatt. Yeah,
And that's for monochrome.
That's for full color.
Full color.
Full color.
So you're always pitching the full color because that's your advantage,
Yeah,
right?
that's our advantage. We use our own converge
Yeah.
solution for this micro display.
Yeah. And do you have like a roadmap where you want to go? Do you want to make it more efficient in the future? Or is like 200 realistic for 2027?
I think the first priority is that we keep improving the brightness. If we have enough brightness, we can lower down the power consumption of the chip. And I think it's the most critical.
It's a priority.
The first priority for the for current markets. And the second one is improving the resolution of the display. And you know, the micro LED has problem of the size effects. If we decrease the decrease the pixel pitch size, and the micro LED emission efficiency will be decreased. And so, if we have a larger room of brightness, so we can improve the resolution, and it's the second priority. And the third priority is the color performance. Yeah. That's we think the market requirements.
So the 320 by 240, that's maybe not the end goal, right? So what is the resolution that you're targeting? Is it like the 640 by...
Yeah, I think the next step may be VGA 640 by 480 is the next step. And we also need to decrease the pixel pitch in order to keep the same display area. Yeah.
So with color conversion, how do you decrease it? So I know like some companies are working on like stacked pixels, right? But you don't do that with color conversion.
Yeah, I think the stacked pixel stacking process is even more challenging and for the mass productions, and because you need to put two different epitaxy layers on top of the CMOS wafers, and it involves a lot of the verification process that will kill the yield of the productions. And so we believe that the quantum dots process is more mature because we use standard semiconductor process to fabricate it, and we use standard photolithography. It's more mass producible. That's what our advantages, and I think it's more achievable and faster for the market. We also have a green and red microdisplay for AR glasses, and you know, green microdisplay is very common in the market, and we also develop our own red microdisplay.
Yeah. So it may be flickering a little bit in the video, but you can see it with your eye.
Yeah.
It's just the...
And for this red color micro-LED is done by color conversion. And the basic is the blue micro-LED, and we put quantum dots layers on top of the blue micro-LED.
Yeah,
so
because the red is very hard to achieve with other materials, right?
Yeah, because for aluminum gallium indium phosphide, it has some reliability problem because the efficiency drops very significantly if the chip the temperature is high. Yeah, so for QD, it has advantages about the stability at high temperature.
Yeah.
And also it can have a very stable wavelength.
Yeah.
Yeah, it's that's advantage.
With QD, I'm not sure if I remember correctly, but there were some problems with the lifetime. Is that still a thing, or is QD is it okay now?
It's conventional. And traditionally, QD has the problem of the reliability, and so normally it's only used in TV backlight as a QD film for full backlights. But because we know this problem and we want to fix this problem, so we have our own material team to do the synthesis and also the quantum dot photoresist for our process. So we know the material itself, and we do the synthesis and try to fix the problem. Also, we mix the quantum dots with the photoresist, and the photoresist itself can protect quantum dot also, so it can apply on top of our micro-LED.
How does it work?
We do photoresist quantum dot photoresist, so we can do the patterning of the photoresist by photolithography process. It's a standard semiconductor process.
Yeah.
So we do everything through the fabrication process, from the blue micro-LED and convert it to the full color microdisplay. It just involves two photolithography steps, red and green, spin coating, photolithography, and also develop to form the patterns on top of micro-LED. That's how we achieve full color pixels. Yeah. In one color pixel, it involve one red, one green, one blue, and two green, because the green composition is large in white color, so it requires two green subpixel. Yeah.
And how efficient is this color conversion? So, how much light do you lose?
Actually, for the quantum dot film layer, the layers and the quantum dot quantum yield, conversion efficiency is around 60% for the film. But after put it on the micro-LED, because we need to make some crosstalk avoid the wall to avoid the crosstalk between subpixel, and it will also decrease the efficiency of the light conversions. Yeah. So we keep improving the light conversion efficiency and also the light extraction efficiency of the device, so we can improve the light output power of
Yeah. Well, thanks so much for the explanations. Thanks for the interview.
Yeah,
thanks for talking to us.
Norman.